We are now on the 5th segment of our taping, and we were looking at this heating curve. It would be a cooling curve in the opposite direction. Now, in the heating direction, this is an endothermic reaction, and in the cooling direction, it would be exothermic. So what I often like to think about when I do these is if I were to put it on the stove to get a transition to happen, it's going to be endothermic. If I would put it in the freezer to get a transition to occur, it's going to be an exothermic process. So for now, let's just look at the endothermic heating curve portion. Now remember, the point at which we have a zero slope, or it flattens out, that's going to be our melting point or freezing point. Same temperature, you should get used to either of those, melting or freezing. And the next plateau or flat point is going to be our boiling point, the point at which it vaporizes. Remember, that's the point at which the vapor pressure is equivalent to the atmospheric pressure. So we would have our boiling point. Now, there's 3 types of processes that involve a temperature change. Steps 1, 3, and 5 all involve a temperature change, and that will be calculated using a formula we call MCAT. We're going to work on those in just a moment. And steps 2 and 4 are done via dimensional analysis. So 1, 3, and 4, we're going to use the formula heat is equal to mass times a constant times the change in temperature. In 2 and 4, I'm going to give you a constant, and we'll use dimensional analysis to solve the mathematics with that constant. So let's go on and see these formulas in action. Now, first off, let's start with ones where there's a temperature increase. In other words, we're seeing an increase in kinetic energy. If we are at a constant pressure, the heat can be equated to the delta H, and we call this formula MCAT. It's a cute little kitty cat because it's mass times a constant called the specific heat capacity. The specific heat capacity is the amount of heat required to raise 1 gram of a substance 1 degree Celsius. Now, we can use Celsius here because we're looking at a difference in temperature. And remember, a difference in temperature for degrees Celsius is equivalent to a difference in temperature in Kelvin units. So we're going to use degrees Celsius. Sometimes you'll see that constant given as Kelvin to the -1 or 1 over Kelvin. But we're okay with using either temperature because, again, we're looking at the difference. So again, the heat capacity is the energy or joules required per gram per degree Celsius that we change. Now, you do not have to memorize values. You do have to memorize the definition and use values in a math formula. So memorize your definition, use values in a math formula, but don't memorize values. And you need to memorize the units. So the definition and the units are things that you are expected to know. Now notice that in this unit, our mass is given in grams. So that means we want to use grams as our unit in our MCAT formula. Now that's the basic MCAT formula. We'll do one of these in just a minute. Let's take a look at the mathematics for the steps in which there are changes of state. If there's a change of state, there's no change in temperature, but we know there's heat involved. So we have to have a way to calculate that temperature, but we can't use MCAT. So these are the flat portions of the graph. You can think of it as a formula, moles times the enthalpy of fusion. All right, the enthalpy of fusion. So delta H is called the enthalpy of fusion. This is the value we're going to use when we are melting, and when we are melting, not we personally, when we're melting an object, it's going to be positive delta H of fusion because that's an endothermic process. When the process is the freezing process, it's an exothermic, so you're going to have to provide that sign. All right, you're going to have to provide the sign for the enthalpy, and this should be a delta here, and a delta there would make that more appropriate, and that should be a delta as well. So make those corrections if you would for me, please. Now, here it's not going to be a problem. The constant's given as a positive. Here you're going to have to supply that sign. So that means you have to have knowledge of what the process is requiring or releasing in terms of heat. If you're breaking intermolecular forces, it's going to be endothermic because breaking forces of attraction requires heat, and it'll be positive. If you're forming intermolecular forces, like you're forming the intermolecular forces in a solid or a liquid, it's going to be exothermic or negative. Now we have a similar thing for vaporization. It's called the enthalpy of vaporization. It's just the joules per mole. And again, it's going to be positive for vaporization because you're breaking intermolecular forces that requires energy, so you'd take that value with a positive. If you're condensing, for condensation, you're forming intermolecular forces, which means energy is released, and you're going to have to provide that negative sign for the delta H of vaporization. And we can plug it into this as a formula if you prefer, or we'll see I'm going to use this delta H of vaporization as a conversion factor. And that is where we will head in the next little video segment. I'll be working some problems for you on this. And I'm going to have you pause in the middle of the video to try them on your own as well. So we'll do a couple of the different types to begin with, and then I want you to take a shot at it.